Welcome back once again for the third installment of the Riemann sums. This is now the midpoint sum. Hopefully you've already watched both the left and right midpoint sum. There are some things that haven't changed in this one. This again is we are still dealing with y equals x cubed. I think we had black before, meaning the color. Whoops, and I'm moving some things around, and I'll just make that black so let's stay consistent a little bit. Alright, so there it is. Things haven't changed, okay? So we have that. We know that our area of our rectangle, nope, still blue. Let's get back to black here. Area of the rectangle is still length times width. We know that our width is equal to delta x, and that formula is b minus a over n. We are doing n equal 4, still 4 subintervals for this example. We do a midpoint, so we're looking at the midpoints of each one. So already you might be thinking, based on our previous videos, what is that formula for x sub I? Well, we'll get there. Delta x doesn't change. We still have b minus a over n, b being 2 over minus 0 over n, which is 4, which is 0.5. Alright, our length is still going to equal f of x sub I, but now we have to come up with a formula for x sub I. Now for the left midpoint, if you remember, our lefts were over here. We had a minus 1 in the formula. Our rights were right here. There was no minus 1. It was just delta x times, it was a plus I delta x. What do you think midpoints will be? Well, you're correct if you said a plus, we're only going halfway, so it's not I minus 1 like before, it's I minus 1/2 for midpoint times delta x. This does not change. This is the same for all midpoint sums. Now the bad thing about this, if you want to, you're not doing too many. This is a very a concept that I really want you to understand, and then I want you to be able to apply it in other situations. So this is not just you know, I don't want you to get caught up on the formulas and think you have to. I really want you to understand the concept of what is going on, especially with these sigmas and summations and these Riemann sums, because it's really, really important as we move and understand what a definite integral is and move from there. Okay? So again, don't get too caught up. So we have f of x sub I. In this case, it's x cubed. In other cases, it may be other things. So we have a, which we know is 0, plus our I minus 0.5. We know our delta x is 0.5. It's all cubed because that's what this is. If this were x squared, this would be x squared. Students in the past they always think it's cubed. No, it's whatever this function dictates. I could have this big long polynomial. Well, this would go everywhere we saw an x in that polynomial. Alright, so there's my f of x sub I. I'm going to just make it a little prettier. Pretty like me. And do something like that. Alright, so there's our f of x sub I. We're going to set up our summation just like before. Same, you might even think like you're watching a rerun here. 1n f of x sub I times delta x. We know that we have 4 subintervals here, so 1 to 4. F of x sub I is this guy right here, so it's going to be this times delta x, which is this delta x, right? It has to be length times width, length times width, length times width. And again, you are going to do the same calculations here. You're going to put 1 in here, you're going to put 2 in there, you're going to put 3, just like we did here with the rights and here with the lefts. Okay, so you're going to have that 0.5, we're going to pull it out again because that gets multiplied to every single one. And I was going to be lazy and not do it, but I'm going to do it. 0.5 cubed plus 2 minus 0.5 times 0.5 cubed plus, I'm going to run out of space. I can see it. You can see I'm running out of space. But I think you understand the pattern, I hope by now. And then, well, I'm going to go off the screen here and do 4 minus 0.5. That's how much I care, is to show you guys how to do it correctly. Close my brackets. When we do all those calculations, we're going to get 3.875 as the answer. And verify it. Go through it. Pause the video and do that. Now, of the 3 approximations we did, and if you watched all the videos, you will know, with our left endpoint, which was our lower sum, we got 2.25. Our right endpoint sum, which was our upper sum, we got 6.25. And then we have this nice midpoint sum of 3.875. What do you think? You would be correct in assuming that this is the best approximation of them all. You ask, why do we do the other ones? Well, some problems are just more conducive to using left, right, or midpoint. And you'll see some, especially when we get to some of the tables and charts, when we get to some of the advanced placement problems where we have to apply this to a chart. We're given a chart of values in a graph. You'll see that sometimes one, is a little better than the other to use. All right, I just want to finish up here, just really connecting this whole idea together. And I know I've mentioned it in class and on the videos, but just give me one more second here. So we have this limits. We have the sum, we have the sum from I going from 1 to n of f of x sub I times delta x. And we're doing it, we've done it in these last 3 examples that you've seen. Same example, just 3 different approximations. That n was 4. But we know that we want the best approximation ever. So the way we do that is we take this limit. And we say, you know what, we're not going to stop at 4. We're not going to stop at 5. Darn it, we're not going to stop at 10 or 11 or 12. We're going to stop at infinity. Stop at infinity. So this is going to go all the way to infinity. So you can imagine, more like this one, an infinite number of rectangles along here. Wow. The width will become a sliver, something that infinitesimally small that you're not going to be able to realize. Well, this, I told you that this becomes an antiderivative, the integral symbol. That's why it resembles that. Now, we are finding the area between 0 and 2, which then become our upper bound, lower and upper bound of our integral. We are going to have f of x, which is just our function f of x, dx, which this becomes dx. You may remember in class that I mentioned that this is a measurable quantity. This is so infinitesimally small it's non-measurable. All right, so we are going to do this. F of x for all of our situations was x cubed dx. You know how to find this integral. It's x to the 4th over 4. What you do not know is the rest. You don't know what I'm doing here. I'm doing something called the first fundamental theorem of calculus, which you do not know yet, and I don't expect you to know. But the first fundamental theorem of calculus, FTC. I'm going to erase that because I don't need that in your minds right now. I just want to show you how this really is affected. So if I do this, I'm going to plug 2 to the 4th over 4 minus 0 to the 4th over 4. That is me computing this using the first fundamental theorem of calculus. 2 times 2 is 4, 2 4s are 8, 2 8s are 16. This becomes 16 over 4 minus 0, which is 4. This is the exact area under the curve. The exact area under the curve. 4. How cool is that? 4 is the exact area. We had one approximation, which was a midpoint sum of 3.875. Not too bad. I mean, I wouldn't trust it if I was using that measurement to launch a space shuttle or something, but not too bad of approximation compared to the upper sum of 6.25 and the lower sum of 2.25. So keep that in mind. And that is where we're going. And I think that's really cool. And I'm hoping you see the beauty in it that I can see of this full circle. Learning this in August and September, learning this in February, March, this in February, and it all coming back to this answer of 4. Well, I hope you enjoyed this video. Again, this is a series of 3 videos, this being the last one. And in class, you'll show me what you've learned. Have a nice night.
David Miller, please.
John Stone out.